Okay, welcome to our first virtual class for CIS 180. Today we will be discussing the second half of Chapter 6 with low-level programming. So just to recap, on Tuesday we talked about machine language, the fact that it is a set of binary sequences or bits that are built directly into the computer hardware. So remember that the hardware needs to operate based on very, very low level, very, very simple, hard-coded sequences that are built directly into the material. Then each piece is unique to its manufacturer. Every CPU is built to recognize different sequences, but again, it's only capable of executing the very most basic actions. Now, obviously, working directly with machine language for coding is absolutely terrible. And with our human computer programmer little game that we played on Tuesday, you can see how difficult it is to try to accomplish higher level, more sophisticated tasks using only these very, very basic limiting commands. So now we move into different levels of languages to give a little more accessibility to that really low level kind of interface. So remember from Tuesday that at the very bottom of our programming language stack, we have the hardware itself with the sequences of electrical signals being passed along. The next level above that is the machine language. The next level above that is assembly language, and then additional languages on top of that. So the languages that are on the lower end of the stack, closer to the hardware, we call low-level languages. The lower level a language is means that it's that much closer to machine code. A computer understands it much more easily, but humans do not. So obviously machine language is an example of low-level language. Assembly is still considered low-level. Any compilers that you make program for are still considered low-level. But the higher up you go on that stack, the closer you get to natural human communication. And that's obviously what we call a high-level language. So Python if you're in programming 1, Java if you're in programming 2, anything that you would typically use today to accomplish a higher level, more abstract goal is considered a high level language. C#, C, C++, Ruby, these are all examples of high level languages. But there are also high-level languages that people create just to be goofy. So some examples of those. LOL code is a language that there's really no point to it. Adam Lindsay decided that this was something he was going to do, and the entire language is basically just internet memes. So the example here, how to output the code hello world. You start your program with the command hi. Ken has studio, visible hi world, and then you end with K thanks bye. So that little snippet is what you would have to implement in order to output the phrase hello world, or in this case hi world. There's another specialty language called Chef, which makes your programs look like cooking recipes. Again, really not any particular reason for it. And here's a sample of that, a little snippet of that. So put cinnamon into second mixing bowl. Like, it's just that kind of thing that people are crazy and want to do fun things just because. So all of these are considered high-level languages because they abstract that need to communicate directly with the hardware and rely on levels underneath them to translate those commands into actual input that the computer can actually use. I believe somewhere there's also a language that's composed entirely of Arnold Schwarzenegger quotes. I don't know what that is called, but I'm pretty sure it exists. But yeah, so any of these would provide a solid little mini research topic for your discussion for this week. So there's some possibilities for you. But on to assembly language. So assembly, again, low-level programming language, but the key distinction here is that instead of having to write actual ones and zeros, we have short keywords and abbreviated hexadecimal notation to represent these commands. So in the examples from Tuesday, writing out all the ones and zeros, binary notation to represent data, it translates to a rather large string of numbers, as we saw. Hexadecimal is a numeric version that would allow us to represent the same number as a binary, from a binary notation in a much, much more condensed manner. So instead of having these many bit streams of ones and zeros to demonstrate a given instruction and the data to use with it, we have short keywords and hexadecimal data snippets that mean the same thing, and they do translate directly down into ones and zeros. A key fact to remember here is that the component that translates these keywords and hexadecimal values to binary is called an assembler. So the assembly language has an assembler. Assembler. There are several different assembly languages to choose from, and they all have a corresponding assembler that will make that translation for you. I believe that the hardware class with Dr. Owen uses MIPS, so that's something if you wanted to look into that later. So remember, this is the instruction format that we saw on Tuesday. The instruction specifier, the first set of bits there, a byte, 8 bits is a byte. And then the second, the operand specifier, which is 16 bits, or 2 bytes, or 1 word. And that's what that represents. Again, the blue block for the instruction specifier is the operation code. The green block is the addressing mode, which represents how to treat the data in the operand specifier. And then the white block is the flex bit, which could be either the 5th bit of the operation code or a bit to indicate what register to use. Remember, if you're using the accumulator register, then the operation code remains 4 bits, and then the 5th bit is a 0, and that tells the computer to perform whatever calculation it wants and put the result in the accumulator. Okay, so how does assembly language work? And the whole foundation of the assembly language environment concept is based on this word mnemonic. I'm sure you've encountered this word before in a language class or maybe in a psych class, but a mnemonic is basically just a way to remember something as far as a general definition goes. In our particular environment, a mnemonic means the short keyword that represents an operation. So if we go back to the instruction format, the 4 blue bits would be replaced by a corresponding mnemonic. The opcode is replaced here. So, for example, in adding values to the A register, the opcode would be those first 4 bits, 0, 1, 1, 1, which stands for the add function. And that 5th bit, 0, means adding to the A register. So in this situation, we would replace those 5 bits with these 4 characters, add A. And that means the same thing. So we are going to add whatever value comes after to the value in the accumulator. Add A. That's our mnemonic. So after your operation mnemonic, you need to have the operand, which is the same as before, the data to be used during the operation. In this case, it replaces the machine code operand specifier, that whole 16-bit block, and we designate with the prefix 0x. I know that's kind of hard to read with this text, but that is a 0, not an O. So it's 0x and then a hexadecimal value. So in this situation, we have this big long stream of ones and zeros, and then it breaks down to 0x008b. So for those of you living in the decimal world, that is the number 139. So remember with hexadecimal, well, in normal decimal, we have 10 digits, 0 through 9. In hexadecimal, we have 16. So it goes all the way through F, I believe, 0 through 9, and then A through F. So having a B in a number, perfectly agreeable. So 008B becomes 139 in decimal. And if you're having any confusion about this, please feel free to email me. I will absolutely, we can meet during chapel or anything that you need to help explain these concepts to you. So after you have indicated what operation you want to perform and what data you want to perform it on, you still need to indicate the addressing mode. In the previous slide, remember, green block here is the addressing mode. 000 means that the value in the operand specifier is immediately addressed. So it's an immediate value, it's an explicit value, it's data in and of itself. And if the addressing mode is 001, it's direct addressing, which means the value in the operand specifier is an address. So the computer must go to main memory to pull that value out instead of using it on its own. So in order to designate that difference here, we add a little suffix to our data operand. So if you want to have immediate addressing, which means that the number 139 is an actual number to use immediately, you add a little I to the end of your operand, and if it's a direct addressing, which means that the value 139 is an address to go to memory to get data, then you add a little D after your operand. So, putting that all together here, stop execution. Again, from Tuesday, we discussed that the opcode for that is 4 zeros. The corresponding mnemonic is simply the word stop. Easy peasy, makes sense. Loading an operand into the A register, adding, subtracting, storing. We represent these as 5-bit opcodes here, even though they are technically 4-bit opcodes. The difference here being the 5th bit tells specifically that we're using the A register. So we include that here for consistency. So 1100 is the load command, and then the third 0, the 5th bit, indicates the A register, which translates to the mnemonic LDA. So again, we include all 5 bits because the mnemonic itself includes that A register dependency, so all 5 bits are included here. Same thing for add operand. 0111 is the actual opcode, and then the last bit, the 0, indicates the A register, which all translates to the composite mnemonic add A. Same thing for subtract, same thing for store. Now, when we get down to input and output, remember, these are actually 5-digit 5-bit opcodes. So all 5 of those bits are actually supposed to be included. And the corresponding mnemonics are char I for input and char O for output. Okay? But now because we are not limited directly anymore by ones and zeros, we can start to introduce new instructions. So we've got here 3 new instructions that we can introduce at the assembly level. The first is branch, which tells the program counter to change. Remember, back on Tuesday, we had 3 different 3 different storage locations which held data. And the first was the program counter, which holds the address of the next instruction to execute. The second was the instruction register itself, which holds a copy of the current instruction being executed. And the third was the accumulator. So what the branch instruction does is it overwrites whatever data is in the program counter and puts in a new instruction. So basically what this does is it derails what the original program flow was going to be and changes it to something else. And this can be very strategic in low-level conditional programming. If you encounter a certain situation and based on one result you want to execute this path, or based on another result you want to execute this path. In higher level languages that would be called an if-else statement. But basically branch allows you to accomplish things like that. Building off the input and output commands that we saw on the previous slide, we also have dec, which is decimal input, and dec-o, which is decimal output. That's a typo on the slide there. But in the same way, with the char-i and char-o, meaning that you can input or output a single letter, with dec-i and dec-o, you can input and output a number. Okay. So some more examples of complete instructions here. I've broken it out according to the mnemonic and the operand and mode specifier, but in an actual program they would all be together. So the LDA 008BI means load the actual number 139 into the accumulator. The second command, add A 008BD, means go to the value or go to the address numbered 139 in memory, take whatever value is in that address location and add it to the value that was already in the accumulator. So in this case, 139. Sub A 008BD means go back to that address at space 139, take whatever value is in there and now subtract it from the value that was in the accumulator. So we're essentially negating the second command that we just executed. And then stop, again, it's a unary operation. It does not have any operands or any data that it uses, so there is no operand, there is no mode specifier. So after executing these 4 commands, we are left with the value of 139 in the accumulator. So now that we've discussed all of these directly impactful operations that you can do directly on data, we now have what are called pseudo operations, which are executed by the assembler itself. So much more complex commands that have no direct equivalent to machine code, but are still very, very helpful in managing the structure and flow of assembly language programs. So these examples here, we've got .ASCII, which represents a string of ASCII bytes. So remember back to the example that we had on Tuesday, where in order to print out the word hello to whatever output venue we were using, you had to actually print the individual characters, so capital H, lowercase e, lowercase l, l, and o. .ASCII allows you to represent actual strings instead of just individual characters. So definitely simplifies your life. .block sets aside a number of bytes for later use in memory. So it allows you to reserve allows you to allocate certain amounts of memory in order to be used for any reason, really. And .word is also a memory reservation operation, but specifically of a word size. So remember, 16 bits equals 2 bytes, which equals 1 word. So it sets aside 16 bits and only 16 bits, but it allows you to populate it immediately with whatever value you provide as the operand. Whereas block, all it does is it just allocates the memory, it doesn't actually populate it. But word allocates and then populates immediately. And then finally, .end represents the end of an assembly language program. So the assembler knows to shut down safely and perform any operations it needs to do on its side to complete the end of a program. Now, I'm sure you've seen comments in different coding assignments and things from Programming 1, Programming 2. If you haven't seen it yet, you will. Comments also exist in low-level languages too. It's always beneficial to have the ability to add this extra text that can be ignored by the translator. So if you've never seen a comment before, basically a comment is exactly what it sounds like. It's just extra information that a programmer can add to a code file that provides additional insight, makes the code more readable, allows you to get rid of certain lines to not have them executed. But basically it just means that the compiler is going to ignore whatever content comes after that reserved character. So in the sample that you see here, this is Java, and the // means this line is a comment. In assembly language, the character is the semicolon. So any text that follows a semicolon, the rest of the line is ignored. Now that could happen at the beginning of the line, that could happen in the end of the line, it could happen in the middle of a line, but anywhere that semicolon is encountered, it's going to ignore everything else. So if you are writing an assembly language program and you're used to Java and you throw in a semicolon, just be aware it's going to create a comment. Okay. So once all the code has been entered, now the assembler takes over. So it takes whatever code you've written, again in assembly language, as input, and then returns the equivalent machine language program as output, so actually ones and zeros. Think of it as an actual language translation process. So if you're in Spanish 1, you may receive a paragraph from your professor as quote-unquote input, and then you have to translate it into English to show your mastery of Spanish language diction and grammar. And once you have the English translation, you return it to your professor as quote-unquote output. And the assembler works in the same way. It's simply taking one program, one set of instructions in one language and translating it directly to another. Most of the time, your machine language equivalent will be much longer than the assembly language version, partially because, as we've seen, the ones and zeros tend to take up a lot more room, but also because with the assembly language being that higher level, I mean, it's still low level, but it's at least higher than machine language, a single assembly command may have an equivalent of multiple machine language commands. So one assembly language command may translate to 3 individual machine language commands. But either way, whatever is provided as the output from the assembler is now able to be directly accessed and executed by the hardware. So how does this all fit together? Really, I don't expect you to know everything about low-level programming. You don't even need to know everything about high-level programming. I just want you to know that these things exist. How do they relate to each other? What makes what possible? So the fact that hardware is only capable of understanding sequences of electrical current. So what power is provided to what pieces and when and where. That's a huge thing that you need to know. The fact that we as humans we don't think in sequences of power currents. So for us, we need to have something that's more accessible. So we layer these languages on top of each other. That you need to know. Assembly language and its format of a mnemonic and what that translates to, that you need to know. So yeah, I mean, the more you know, the more equipped you are to incorporate this knowledge into whatever you choose to do. If you end up as a software engineer, you will have much greater appreciation for what you're doing if you understand that at the bottom of all things, somebody went through a lot of trouble to make everything talk to the computer the way it does. So it's really just about instilling appreciation in your minds that this is not something you have to do every day. But having said that, if it is something that you do end up doing, now you have a greater idea for at least what strategies you might be expected to know of down the road. There's a lot of research being done nowadays on power consumption for different computing elements. We've gotten to the point where we're pretty limited with regard to the physical hardware improvements that we can make for computers. Transistors can't really get much smaller. We're down to, I think I said on Tuesday, 14 nanometer wide transistors on a given microchip, which is about 42 silicon atoms across. So if we wanted better performance in previous years for our computers, we would just throw more transistors on a microchip. But now we're getting down to the atomic limit of what we are able to push onto a microchip. So now we need to get more strategic on how we interact with these transistors at a really low level, which could be where you end up. If you happen to be in a research lab that that deals with power consumption and instruction latency and these like really small things, this is where you might spend a great deal of your time. So now that we've put all of that together, we can interpret a given program. So you can see here I've built a little program that has the comments explaining what's going on. So BR main, meaning we branch around our data declarations there and go directly to the line of code labeled by the word main. So LDA, load into the accumulator, the value of D, the addressing mode of D, which means direct, which means the value designated by the word sum. So going back up, sum is a word, so 16 bits, and then the value that we put into that memory location is the value of 0. But then we also have 3 additional values, a block of 2 byte block for num1, num2, and num3, and those are just memory locations. There's nothing in there right now. So let's go back down below. So LDA sum D, load the value that is designated by the address sum into the accumulator, which is 0. Des I, decimal input, number 1D, which means we're going to prompt the user for a numeric value, and then we're going to store it in the address location that's designated by num1. Add a num1D means we're going to go to memory, take the value that the user provided that is stored in num1, and add it to whatever value was in the accumulator, which at this point was only the value of sum, which is 0. So if the user entered a value of 2 for this first input, that means that the accumulator now has a value of 2 inside it. We then repeat the process for num2 and num3, prompting the user for input, storing it in that previously allocated memory space, and then adding whatever value the user provided to the value in the accumulator. Finally, down near the bottom, we have STA, which means store A. So we take the value that's in the accumulator, whatever sum of the numbers the user provided, and now put it back into that memory location designated by the label sum. And then finally at the end, des-o sum D, take the value that was stored in sum, print it back to the user, stop processing, and end the program. The code isn't perfect. It is very repetitive. Comments in general, you're not going to see this explicit kind of commenting pattern, but at least it's here to show you what the code is doing, gives you the idea. So at least if you are able to look at an assembly language program and recognize what the goal, what the general operational output is going to be, I will be very happy and you will do well on exams. Okay, more instructions. All right, BRLT accepts an address as the operand and updates the program counter to point to that address if the A register is less than 0. So remember back to a couple slides ago talking about the branch instruction that resets the program counter, giving it a new value, and then after the current instruction is done executing, now we go down a different path than we were before. So this right here is a conditional branch, which means that if the value, depending on whatever value is in the accumulator, that determines whether or not the branch is actually taken. So the actual updating of the program counter does not happen until the accumulator comparison passes. So in this situation, if the accumulator is less than 0, LT, BRLT, less than 0, then that is when the operand value is copied into the program counter. That is when we actually change the execution path of the program. BREQ is a similar command which compares the value in the accumulator to 0. So the key here is EQ, equal. So you have LT less than, EQ equal, and they're comparing to 0. So again, we only update the program counter if that comparison passes. If the A register value is less than 0 or equal to 0, respectively, then the program counter value is updated so that the next instruction that is executed after this one is the updated branch path. So here we go. Another little program to interpret. We've got the same kind of thing with receiving input from the user, reading in values, loading into the accumulator, storing up a sum, etc. But the difference here are the branch statements near the bottom. So we've got a branch EQ, BREQ statement and a BR loop statement. So rolling down from the top, BR main, so we go to main, starting at des I limit D. So inputting a numeric value from the user, which indicates a limit, then rolling to the next command, des I num D. So reading in a value from the user, any number will do. Load that number into the accumulator, then add whatever value is in sum to the accumulator. So at this point, sum is 0, as you can see from the top. This is the first time through the code. So loading the number, whatever number the user provides, into the accumulator and then adding 0, the value is just whatever number the user provided. So next we're going to store whatever value is in the accumulator into sum. So basically what happened is we have incremented sum by whatever number the user provided. And then we're going to load the counter into the accumulator, which is, as you can see above, a word, 16 bits, which starts at 0. So we're going to reset the accumulator to that counter value of 0, and we're going to add 1 to it, and then we're going to store that value back in the counter memory. So at this point, we can see an example of how you have to do very repetitive, very, very specific statements to do what would have been considered a very easy single line command in a language like Java. If you wanted to store a variable and increment it by some number provided by the user, you could do a code line like sum plus equals num, and that's your whole command. So whatever value is already in sum, you add the num value to it and then store it back in the sum variable. But for this particular example, that requires 3 different commands: load A, add A, and store A. In the same way, if you wanted to increment a variable value by 1, in Java, it would be simply counter plus plus. But in this example, you have to load the value of counter into the accumulator, add 1 to it, and then store it back in that memory location. So that's another 3 commands. In this vein, we're now going to compare the limit that we received from the user in that very first line against the value in the accumulator. That is a command that we did not explicitly cover, but in this situation, I think you'll forgive me. So whatever value is in the accumulator is the updated value of counter. So the first time through, counter was 0 initially, then we add 1 to it, and now it's a value of 1 in the accumulator. The store command is a little tricky. It sounds like we're taking the value from the accumulator and directly storing it in memory. In reality, we are simply copying it. So taking the value and storing it in the memory address of counter does not remove that value from the accumulator. It's still there until we overwrite it. So by executing the store command and then the compare command right after each other, we are still able to access that updated value of counter that was in the accumulator. So if the user provides a limit of 1, meaning they only want the loop to run once, then the value of this compare will be -1. So in that case, branch equals will, that is another typo, apologies. So that should be branch less than finish, actually. So basically what will happen is it will compare the value of the accumulator, and depending on the result, you will either go to the finish line or you will branch back up to the loop and run the loop again. At the finish, you will output the sum to the user and then stop and end. So it's really a very appropriate example, I think, of showing what kind of convoluted logic would be necessary to accomplish these higher order, more complex logic than would be necessarily desirable at such a low level. Basically, what we saw on the previous slide is an example of an algorithm, and we will go in more in depth with this next week. But an algorithm at its very, very basic level is a logical sequence of steps that is taken to solve a problem. There are a number of different commonly accepted algorithms that solve very specific problems, and you will encounter these more directly in your data structures and algorithms class with Dr. Rohrbaugh if you're a computer science major. I'm not sure that the digital media majors have to take that class. But the exposure to algorithms in general and the benefits of learning to think algorithmically, learning to think according to, learning to problem solve according to a logical sequence of steps will benefit everyone, especially if you are going to take more computer classes, and specifically programming classes. One particular way that you can achieve algorithmic problem solving without actually writing code is through the practice of pseudocode, which we will go into again next week. But it's basically just using common language to represent the different steps of your algorithmic solution. So if you know, for example, that you want to have a particular function executed if one condition is true, but a different one to be executed if it is false, you would say if shoe size greater than 9, and then designate what functions you want to complete, else whatever. So we will talk more about that on Tuesday. A little bit of an example that might help out a lot. If you're a sports fan and you are attempting to describe the practicalities of a game to someone who doesn't necessarily understand, you're not going to go into great levels of detail when trying to describe what happens and when and where and why within a given game. You're going to speak in layman's terms, so to speak. And believe me, I've had that quite a lot with friends trying to explain football to me. So in this way, think of it as trying to explain Hail Mary to, I don't even know what that is, to a friend who doesn't get football, like me. So it's good for working with teams, it's good for brainstorming on your own, it's good for identifying where in your programs you may need additional comments, that kind of thing. But again, we will get into that a little more on Tuesday. For now, be aware of these pseudocode components. What information would you need to effectively detail, structure, identify the components of your pseudocode? It's always good to highlight where your variables are. So remember, a variable is a name that we assign to a memory space. So it would hold data, it could hold another address, it could hold any amount of things, but naming a given memory space allows us to more effectively organize and understand our code based on what the data is going to be used for. Along with variables, you also have assignment statements, which would either set or update the value associated with a variable. And this is going to be a key thing to highlight in your pseudocode and make sure that you are performing assignment correctly and at the appropriate time. The third component would be instances of input and output, making sure that you know when you are going to request information from the user or when you're going to display it back to the user, making sure that those statements are appropriately indicated and strategized. That's a huge part of pseudocode. Also, like I said before, with conditionals, like the shoe size example, making sure that decision points are appropriately indicated in your pseudocode to make sure that the different possibilities of program flow are appropriately represented. So make sure that when writing pseudocode, your selection statements are given appropriate consideration. In keeping with selection statements, you also have repetition statements. And these both operate off Booleans, which basically is a condition resolving to either a true or false value. So if shoe size greater than 9, if day of the week is Wednesday, if whatever, any expression that's true or false is a Boolean. Any Boolean can be used in conditionals or loops. So with a repetition or a loop statement, pseudocode allows you to identify conditions or sets of actions that could be repeated until some sort of other event occurs, until a given condition is met. So with these in mind, we're going to propose a challenge. This is not a requirement. This is simply an extra thing, an extra activity you can do if you desire a little extra thing to work on. So in this challenge, write a pseudocode program, not an actual program, a pseudocode program that prints the numbers 1 to 100 with the following conditions. So for multiples of 3, so like the number 3 or the number 6 or the number 9, instead of printing the number, the program should print the word fizz. So number 1 and number 2 are not multiples of 3, so you would print 1, then 2, then fizz. For multiples of 5, 10, 15, etc., you would print the word buzz. So it would be 1, 2, fizz, 4, buzz. Then for multiples of 3 and 5, instead of the number, you would print fizz, buzz, both of them. So for 15, the number 15, it would be 13, 14, fizz, buzz. So yeah, so that would be just a fun little activity that if you want to chew on that for a while. Be aware of conditions in this situation. Be cognizant of what order you are evaluating your numbers in. So for example, how do you control whether a given number is printed a given way if it matches more than one condition? And so in this particular example, multiples of 3 and 5 might give you issues if the number satisfies an earlier condition. So 15 would satisfy both multiple of 3 and multiple of 5 conditions. So instead of printing fizz buzz, you might only print fizz, or you might only print buzz. So something to be aware of, something to play around with. Let me know how it works out for you. Again, not required, just for fun. Okay, finally, we're going to talk a little bit about testing. So testing is one of the greatly undervalued skills in the software world. I personally don't really like testing. I would much rather build things. But if you are a person who you just really like getting into the guts of a software suite or a new product, and you just like playing around with it and seeing how it works, there are full-time software engineering positions just for testers. And I actually have friends where that's all they do. They do testing, and they love it, and they have a great time. I believe that the programming classes and different computer science classes are now starting to employ test-driven development with writing code specifically according to test plans, which is very nice and very, very helpful. So we're just going to give a little overview on the kinds of testing that you might encounter and how you can set that up properly. So testing, never going to go wrong. Every piece of code that you're going to write, it could be the absolute best code in the world, but if you never test it, it's nothing. You need to test. You always need to test and try to think outside the box and how things could or would go wrong, and you're still going to miss things. So the first line of defense is what we call desk checking, which means tracing the execution of a program out on paper. In our situation, in our test case here, that's the algorithm. So by writing out your algorithm on paper and making sure that you understand those components that we covered earlier, what variables you're going to use, what assignments they're going to receive, what conditions or loops they're going to run through, what input and output you're going to get from the user. If you can think through all of those components and make sure that they all line up in your head and are doing what you think they will, when you think they will, that's your first line of defense in writing good code. Your second line of defense is your actual test plan, which would be a formal document detailing all of the actual tests that you would complete in a formal environment on a given program. So in a software engineering team, you would actually have a document, a printed up little Word doc that says when you are ready to release a new version of the software, these are all the steps that you have to go through and all the conditions that you need to test for in order to verify that the code works as it's supposed to. And when you do that, that's called the implementation of a test plan. And those can take quite a long time, hours and hours, up to a week, depending on all of the different components that are involved. But it covers things like entering negative numbers instead of positive numbers, hitting enter to submit a form instead of clicking a button, using Internet Explorer instead of Firefox. There are so many different things that a user can do that the programmer would have never thought of. And I'm sure that you've encountered in your time buggy software, buggy websites that you try to do something that obviously wasn't intended, and now the code has broken. So it's that kind of thing, just covering all the bases, making sure that the code fails gracefully, even if there's nothing else that it can do. So there will definitely be certain times when the user will try to complete an operation that is just not acceptable. So for situations like that, you still need to be able to give them appropriate error messages and continue on with whatever you were trying to do. So when you are actually completing your testing, there are two types to be aware of. white or clear box testing, which gives the tester all of the information they need about the code itself to make sure that the test plan executes every line of the program by the end of the implementation. Now, this might require you to do multiple run-throughs to cover different conditions or different loops, because it may very well be possible that in a single run of the code, you cannot physically hit all statements in the program. So you may be required to run through multiple times, configuring the program in different ways, giving it different inputs, but by the end of the whole test plan, you should hit all lines of code. And this is why it's called code coverage testing, to make sure that all statements are executed, everything has been touched at some point. The opposite of that is called black box testing, in which the tester has no idea what is happening under the covers, so to speak. The image here is of giving some input to a black box, which shakes around and does something, but you don't know what, and then your output pops out on the other side. So in this case, we don't know exactly what's happening inside the box, but we know what we're providing as input and what we're getting as output, which provides the name data coverage testing. So the emphasis with black box testing is more on all different kinds of possible combinations of inputs and outputs, all kinds of data coming in and going out. Automated unit tests are very helpful with different kinds of white and black box testing. Testing in and of itself can be very repetitive. So in different languages and frameworks, there have started to be greater support for automated testing, for writing additional code that's going to test the code that you wrote before, which makes testing so much easier, and I'm so glad they have that. So yeah, we've covered assembly language, talked about it as an abstraction of machine language. We've talked about the different mnemonics and the kinds of operations that you can execute in an assembly language environment. We talked about the different pseudo operations that we can do. We've looked at different code examples for assembly language. And we've talked about algorithms, pseudocode, and testing. So remember, for the homework for this week, research a topic of interest that you have for the history of programming, whether it's a person who made particularly meaningful contributions, a groundbreaking computer in and of itself, or a language that you really like. Make sure that you post the summary and questions to Canvas for your classmates to answer, and then make sure to go back and answer questions posted by your classmates. And this has the same typo as the other set of slides. It is not due midnight October 11th. It is due 10 minutes before the start of class on Tuesday. So speaking of class on Tuesday, we will gather in our classroom as normal. Don't forget to read the next chapter, which is chapter 7, and take the chapter quiz. It is also due 10 minutes before the start of class. So have a great weekend. Can't wait to see you on Tuesday. Take care, guys.